Good morning, dear, and welcome back. So, you have started watching videos on genetic algorithm, and the other day we discussed some basics of organic evolution, um, taking a digression from exactly describing genetic algorithm. But the digression was justified in the sense that you know now some basics of organic evolution, right? And since Mother Nature, we assume that Mother Nature optimally changes its species. These are our assumption and assumption backed by the facts which we see in the Mother Nature, because Mother Nature so far optimally has produced the most intelligent creature like human being with so much complication in the machine itself, and we are the most intelligent creature. Well, it's debatable, but we think that we are the most intelligent creature. Anyway, Mother Nature has developed through millions of years of evolution, right? And we are trying to copy the same for getting optimal solution, the best solution, okay, of a problem, using the same steps in silico, that is inside computer, right? So here actually you have seen some of the concepts you have already know that this is called chromosome. Chromosome resides inside the nucleus, right? And we have 23 pairs. But for genetic algorithm, you can have anything of your choice, okay? It could be 4-bit chromosome, it could be 8-bit chromosome, it could be 16-bit chromosome. Here, let us say 1, 2, 3, 4, 5, 6, 7, 8. So 8-bit chromosome, right? So chromosomes, and these are called actually genes 1, 0, 1, 0. This is an example of binary coded genetic algorithm. As I told you that for genetic algorithm, first you need to understand the problem, whose optimization solution you are trying to um, determine using genetic algorithm, and then you need to design the chromosome, that is whether 8-bit or 4-bit or 16-bit. Okay. More number of bits, more sophisticated solution it will be, because more variations will be there in the offspring and all, you will see, but computationally it will be complex. So let us see, actually in biology, what are those nucleus chromosomes, where they reside actually. See, this is a cell, this is a cell body. Just funny thing is as if it's a living one. And inside the cell you have nucleus, and inside the nucleus you have chromosomes. Okay, and chromosomes, some part of the chromosomes they call gene. Okay, so this could be a gene, this could be another gene. Gene actually carries the hereditary material or genetic material, and that consists of DNA, deoxyribonucleic acid. Okay, so this is in biology, and in silico we consider this is DNA, this is chromosome, okay, chromosome, and these are the genes. Okay, for example, or inside gene there will be DNAs, but here it is, we consider them as DNA or whatever, right? So this is the structure of a chromosome. Okay. Also, you know that this is a little bit history. 1970s, actually, John Holland introduced the concept of genetic algorithm. So his aim was that to make computer do what nature is doing, and his concept concerned with the algorithm that manipulate the string of binary digits. Okay, so each artificial chromosome consists of a number of genes, and each gene is represented by 0 or 1. So this is, I think, 16-bit 1, 2, 3, 4, 5, 16-bit chromosome, right? And these are called genes. So this is a binary coded genetic algorithm. So the moment you get a problem, optimization problem using genetic algorithm, which is an evolutionary computing optimization method, right? You will have to codify your problem. So, and then you will have to evaluate. So code means this is your decision that I think my problem will be better solved if I consider a 16-bit chromosome having 101010 randomly. Okay, they are called genes. So our objective is nature has the ability to adapt, and then GA will also have the same ability to adapt, and through encoding and proper evaluation we can reach to the solution. So here to evaluate I need a fitness function. If you remember Darwin's theory, right? So there will be survival of the fittest. How do I know in silico who is the fittest, right? Here fittest means which chromosome is going to survive. Okay, for that, for evaluation, we need to create a fitness function, okay, where I will test every individual chromosome that where they stand. So very well it is actually in a simplified way it is done. Fitness function could be hand design, and many times it is done designed with the error function, but some kind of function is needed so that chromosome will be tested against that function. And you remember in linear regression also we had some kind of function, error function, and square error function actually, because we thought that that's the function where parameters are there, and if I can consider a quadratic function like this, x is a feature, I think you remember, right? So h parameters by w x, right? So w we are trying to get by running an optimizer, stochastic gradient descent algorithm or gradient descent algorithm. So basically our objective was to reach here, and corresponding to this point, whatever w is there, we took that parameter, right? So analogically similar, you need to have a fitness function. You will have to design a fitness function. Indirectly it influences the problem. They are also indirectly, in logistic regression, for example, the fitness function, the objective function was cross entropy function. So you all know that was for tuning the parameter, right? Here that fitness function is needed to test that which chromosome survives, right? And then we run, actually once you have fitness function, then GA runs like that. We select chromosome, we choose number of chromosome, then we allowed mating, that is reproduction takes place. So our intention is to create stronger and stronger offspring. How do I know which one is stronger? Because now I have a fitness function, I will test each chromosome against that function, and whose value is bigger, that chromosome is fitter. So that's our in silico assumption, right? Here, in a simplified way, this is a flow chart. Okay. So this is a flow chart of, say, I have any problem, f of x equals to, say, 15x minus x square. So this is the unconstrained optimization problem, hand problem or toy problem, because this is not to be done using genetic algorithm, but we are trying to understand how genetic algorithm can optimize. So this is the unconstrained optimization. I have only a function, quadratic function, and I know it's very simple. by gradient method you can figure out for what value of x the function is optimum. That you don't need genetic algorithm. But using genetic algorithm, this is a toy problem. We are going to learn genetic algorithm using this toy problem. But before doing that, let us see how the flowchart, through flowchart, how a genetic algorithm works. So initially you start, then you need to create a population of chromosome size n, right? So population is maybe x1, x2, x3 up to xn. So these are called chromosome. Each x1, x2, x3 actually you decide that they are chromosome if it is 4-bit, okay? So this is x1, okay? Then x2 will be similar kind of 4-bit. So it may be 1 0 1 1 1 1 1 0 anything, right? So these are your codification. You need to do that. That you need to select the number of chromosome, not only size, the 4-bit, and total number of chromosome you need to also select. And once you select a number, they are not going to change over population, right? Say you have selected a number of chromosomes, and then each chromosome x1, x2, x3, and say they are binary. I am giving an example of binary coded GA. So the gene can only take place, only gene value can only be 0 and 1, inside the chromosome. Okay, so this is called binary coded genetic algorithm. Now, which one is better to know? Okay, I will have to calculate the fitness value. Okay, of each chromosome. Okay. And then you will have to select some termination criteria. For example, the fitness value is not changing anymore appreciably. If this is the case, yes, then stop. That's your, those chromosomes are your answer. But if it is no, then select a pair of chromosomes for mating. Okay. Then exchange parts of the two selected chromosomes and create two offspring. Okay. And then randomly change the gene, change the offspring, and then you create fresh chromosome, and you test again against that fitness function, and you continue to do that till you are not getting appreciable changes in the fitness values. That means in case of, it is a search algorithm, right? In case of when it may happen, say I have a function like this. So this function normally is not, you see, quadratic in nature. So there will be many ups and downs, local optima, right? So if suppose you are doing this repeatedly and the fitness value of the chromosomes are not changing appreciably, then what does it mean? It means your search is trapped inside the local optima. So to come out from the local optima, we use the concept of mutation. Mutation is a genic change. Okay, so randomly we just replace 0 to 1, 1 to 0, like that. And in doing so, it may happen that you have developed a very poor chromosome, but never mind. It will allow you to come out of the trap and then again run the basic GA, that is crossover mating, and testing with the fitness function. So that's the idea, that gene value into two offspring chromosome randomly, and then see, then place the resulting chromosome in the new population. So is the size of the new population equal to n? It has to be n. Yes, then replace the current chromosome population with a new one, and then you go ahead and repeat. If no, then you will have to create again pair of mating chromosome for mating, and till those chromosomes will be only kept which which will be number of which will be same generation after generation. Okay. So this is very simple, right? Isn't it? Very simple genetic algorithm. Let us try to understand. So this what I have told. Um, uh, that crossover probability, PC, mutation probability. Mutation is very rare phenomena. Only you use it for making your algorithm come out from the local optima trap. Okay, so this has to be carefully done. It is very probability is very small, 0.001 or maybe 0.001, very small probability, because mutation is not desirable. It can give poor solution, but time to time it is desirable, because you never know. Since you have a function, unknown function you cannot see, you assume that there are local optima, and the algorithm, if it is trapped in the local optima, to come out from there you can use the mutation operator. So you have two operators now: crossover operator for mating and mutation operator for making algorithm coming out from the local optima, right? And then you see fitness function you have to define, and that's the very important function, how to design a problem specific fitness function. If you can design a problem specific fitness function which requires a lot of experience, then that's great. If you don't, then some kind of error function you can design, problem specific error function, and error function can act as a fitness function. So those chromosomes which will give less value of that error function are the fittest candidate, like that. Okay. So you can randomly select the number of size n, and then calculate fitness function of each individual chromosomes. Select the pair of chromosomes for mating from the current population. Parent chromosomes are selected with the probability related to their fitness value, and then create offspring chromosome by applying genetic operator, crossover and mutation. Place the created offspring chromosomes in the new population, and then repeat this step 5. That means again you select a pair of chromosome for mating. Current population, parent chromosomes are selected, the probability related to their fitness. Okay, so like that, replace the initial chromosome population with the new population, go to step 4 and repeat it. So whatever I showed you in the flowchart, we have explained here. Okay. Now let us try to understand by solving a hand problem. Okay. By the way, you can refer to our textbook. Okay. The name of the book is Artificial Intelligence, a Guide to Intelligent System, written by Mikhail Negnevitsky. We have several copies in the library, so you can get reference, more information from there. But try to now understand how a basic genetic algorithm works. So after understanding this, we'll also discuss why it works using schema theory. But right now, concentrate on this. So I have a function 15x minus x square. Okay. So this is a fitness function. It's very simple toy problem. In actual problem, you need to define this function, but assume that it is there, and you have been asked to figure out what is the value of x which will actually maximize this function. As I told you that this function is not suitable for to be solved by genetic algorithm, because very easily it can be solved, and just differentiate and make it equal to 0, what value of x is there. So you know, right? So equal to 15 minus 2x, that equal to 0, so x equal to 7.5, right? So this is the solution we know. Then you can check that whether it is maximum or minimum. That means you need to figure out x equals to -2. So whatever solution you will get, that corresponds to maximum. So this is simple calculus method, unconstant optimization. You can easily solve it. But we will solve the same problem, which is easy to solve by other means, using genetic algorithm, so that we can understand every step of genetic algorithm in solving this problem. So you take your notebook and then see how to move forward. First, I need to encode. So you need to first decide, okay, where parameter x varies between 0 and 15. For simplicity, you may assume that x takes only integer value. Thus, chromosome can be built because my x lies between 0 and 15. Within that, you will have to figure out what is the maximum value, and I already know, and we will see whether genetic algorithm can also give similar kind of result, right? So first, you need to figure out the chromosome size. Here 4-bit chromosome size is good enough, because 4-bit can accommodate any number between 0 and 15, and x value will be 0 and 15. So, and this is binary coded. I have decided that all the values in the chromosome, the genes so-called, either 1 or 0. So this is called binary coded gene. Also, I decide, so it's a design problem, a lot of decision you will have to take, that I will take some, say, 6 chromosome. 6 chromosome I will take, and out of all this, so these are the chromosomes, right? So which 6 I can select? Okay, initially, randomly. Okay, randomly you can select initially. Okay, or if you want that right from the beginning, so each chromosome has a fitness value, because this is what 2 to the power 0, 1. This is equals to 1. This is equals to 2. This is equal to 3, 4, 5. This is 6, 7, so 8, 9, 10, this is 11. So you put those values, okay, here, and see the fitness. So this, if this is the chromosome, what is its fitness value? 15 minus 1, 14. So you write 14 fitness value. So each chromosome you can calculate fitness value, and take those chromosomes which are among the top fitness values. Okay. So, and you suppose you have decided that I will select a population size of 6 with crossover probability 0.7 and mutation probability equal to 0.001. So we will start from here in my next class, and I will show you how beautifully by hand you can understand, by doing by hand you can understand all the intricacies of a genetic algorithm, how it works. Okay. Till then, stay safe and have fun. Bye bye.